I am accustomed to speak with a chalk and blackboard, so this is something unusual for me, even using a projector, let alone a PowerPoint, right? Okay. We start with an elementary notion of what is called a finite information source, which consists of an alphabet, which is a finite set, and a probability distribution on the finite set, which is denoted here by the letter mu. So, it is a very elementary statistical experiment. You perform the experiment, the outcome is a letter from the alphabet, and the probability for its occurrence is mu of x. If you perform the experiment and the outcome is x, you ask the question, what is the information you have gained? Imitating an old idea in statistical mechanics from Boltzmann, Claude Shannon proposed that the information that you gain by observing the outcome x is equal to minus log mu x. So, it has an average value, which is the expectation of minus log mu x, which is there as h mu equal to minus mu x log mu x. But whenever you look at expectation, it is a common practice in statistics to also look at its fluctuation. So, you also look at the variance of minus log mu x, which I have denoted here by sigma mu squared. It is also expressed there. Both of them, both the quantities h mu, namely the Shannon entropy h mu and the fluctuation of minus log mu x, which is denoted by sigma square mu, both of them share the additivity property. Namely, if you perform two independent experiments where you have an alphabet A1 with distribution mu1 and then A2 with mu2, and these are performed independently, the distribution is denoted by mu1 tensor product mu2, and then the information contained in the product or information contained in the joint experiment is h mu1 plus h mu2, and the fluctuation is also additive. The fluctuation in information sigma squared mu1 tensor mu2 is sigma squared mu1 plus sigma squared mu2. Now, you have A and the probability distribution mu, but usually in many problems A is a very large set, or you repeat the same experiment n times, and then you have now a new alphabet A to the power n, and you have mu tensor product mu n fold. So, the size is increasing, but most of the probability will be concentrated in a small region, and from an information theoretic point of view, it is only the smaller region which is of great interest. So, I introduce an important definition which is here written as 3. N mu epsilon is the least, you consider every set E contained in the alphabet whose probability exceeds 1 minus epsilon, where epsilon is a pre-assigned small quantity, positive, lying between 0 and 1, and consider the minimum of that. And that depends only on mu and epsilon. So, n mu epsilon is the smallest set of smallest cardinality on which at least a probability of 1 minus epsilon is concentrated. And we want to have an idea of this number n mu epsilon, because if I want to transmit information through any kind of channel, I will use smaller code words for the elements coming from this set and larger code words for elements outside this set whenever I want to communicate machines. So we want to have an idea of n mu epsilon, and I have exhibited here two inequalities, n mu epsilon, and it is entirely in terms of h mu and sigma mu. So they are the two important parameters from an information theoretic point of view whenever you consider any finite statistical experiment. So this n mu epsilon cannot exceed this quantity. That is the lower bound, and you also have an upper bound in the second inequality, and it is slightly more complicated, and the proofs of both are extremely elementary. You need only a knowledge of what is called Chebyshev's inequality in probability theory, which is usually, I think nowadays, taught even in schools. So thanks to Chebyshev's inequality, by a clever use of that, you get two important bounds. Now suppose I repeat this statistical experiment n-fold, then A becomes A to the power n, n-fold Cartesian product of A, mu becomes mu to the power n, that is n independent experiments. Then what happens to this number? Then of course n mu epsilon, n mu power n epsilon will also grow exponentially. So you take the logarithm of that and examine how it grows, and that is going to give a kind of index, like the Lyapunov index which you use in differential equations or general theory of linear transformations. So the logarithm of this number, namely logarithm of the size of the smallest set which contains probability greater than or equal to 1 minus epsilon, and that logarithm minus n times the entropy, the Shannon entropy or Shannon information, divided by root n. If you scale it, it's like very much in the spirit of the central limit theorem in statistics. So if you look at it, and then you look at the limit inferior of this and the limit superior of that, and see where exactly it lies, these two quantities lie. The limit inferior is always less than or equal to limit superior, and you have the third inequality, and you see it involves again the description of the estimate involves the entropy h mu and also involves the fluctuation of information, namely sigma mu square, as in central limit theorem. And as a consequence of this delicate estimate, you get the first theorem of Shannon, which he proved in 1948 in his famous paper in the Bell System Technical Journal. And that is the logarithm as divided by n, limit n tending to infinity equal to h mu. But the estimate which I gave earlier, it tells you also about the speed of convergence. How fast does limit, as n grows, how fast does this converge to h mu, and that this, the inequality 3 which I gave earlier tells you that the rate of convergence is 1 upon root n. That is the difference between the left hand and the right hand side tends to 0 at the rate of 1 over root n. Now let me look at the quantum case. Again, the elementary quantum information source, which I have abbreviated as EQIS. Alphabet is now quantized. Whenever a set is quantized, it becomes a Hilbert space. If a set A of cardinality n is quantized, in quantum theory it will become an n-dimensional Hilbert space. It is always a complex Hilbert space. And then earlier you had a probability distribution, but now you will have a density operator. That is a state of the quantum system. Then there is a famous quantity which was introduced by John von Neumann in his famous book Grundlagen der Quantenmechanik in 1932, where the entropy in the thermodynamical context was introduced as S rho equal to minus trace rho log rho, but here I used base 2 because we are in information science. We always use the logarithm to the base 2. Earlier it was the expectation of minus log mu, but log mu is now replaced by log rho, and that is a Hermitian operator, and its expectation you compute according to the quantum rule, so it is minus trace rho log rho. That is the von Neumann entropy. And for studying fluctuations in the this is also a kind of Shannon-like information. And again, go to the fluctuations, you have to compute the variance of log rho, which means trace log rho log rho square minus S rho square. S is the expectation. So you subtract the square of the expectation from the expectation of log rho square. So you have again two quantities, the von Neumann entropy and the fluctuation. And now these two quantities also have additivity property. Two independent quantum system means you will take the product of the states, tensor product of the state. Then you have S rho 1 tensor rho 2 is S rho 1 plus S rho 2, sigma squared rho 1 tensor rho 2 is sigma squared rho 1 plus sigma squared rho 2. Both of them are additive. It is like if you have two independent random variables, variance of x plus y is variance of x plus variance of y. So it is the same kind of property here. Now I have the state spreads the probability over the entire Hilbert space. But most of the probability can be concentrated in a subspace. So whenever I have a subspace, I look at the projection on the subspace. And then if I want to compute the probability, I will compute trace rho multiplied by that projection. Right? That is the amount of probability concentrated in the portion on which P projects. So if you do that, P is a projection in H, trace rho P exceeds 1 minus epsilon. Consider all possible such projections. And for each projection you look at the dimension. Earlier we looked at cardinality. When you quantize, you will look at dimension. And then compute the minimum of all possible, minimum of the dimension of all projections which under the state rho have probability greater than or equal to 1 minus epsilon. If you do that, I have a number n rho epsilon. So instead of n mu epsilon, now you have n rho epsilon. And the same pattern. And you need only classical probability theory in order to get at the three inequalities which I expressed earlier in the classical situation. And if you follow carefully, the arguments based on Chebyshev's inequality, once again you get three parallel estimates. N rho epsilon, only the Shannon information or Shannon entropy has been now replaced by von Neumann entropy, and the sigma mu squared has been replaced by sigma rho squared. And I have an upper estimate for N rho epsilon and I have a lower estimate for N rho epsilon. Now I look at an n-fold product of this system. So now rho is replaced by rho tensor power n, and now I look at n rho tensor power n epsilon, namely the projection of the least dimension which contains, according to the state rho tensor power n, a probability greater than or equal to 1 minus epsilon. Then you have the limit inferior and the limit superior fluctuate between minus sigma rho by root 1 minus epsilon and sigma rho by root epsilon. At here, unfortunately, this table space is so little, I cannot search for my arm. Right. You can now compare the earlier estimate. Its fluctuation is between these two limits, and now the fluctuation is between these two limits. So you have an analog of this, and if you go back to the Shannon's theorem and do the same analysis, then the limit of the logarithm of this number n divided by n, that is von Neumann entropy. So it gives you an interpretation, an information theoretic interpretation of von Neumann entropy. Namely, as you repeat the experiment and if you look at n rho tensor power n comma epsilon, it behaves like e to the power 2 to the power n times von Neumann entropy. This is the theorem of Schumacher in 1995, but I have given precise upper and lower bound, and the speed of convergence here is once again of the order 1 over root n, with even you can even estimate the constants involved in the order. So having described the Shannon, for obvious reasons, he called that particular theorem as the noiseless coding theorem, and Schumacher calls this the noiseless coding theorem for storing quantum information. Right? But we have very little time to go into the philosophy of all that, but I will give at the end a reference wherein everything is given in the greatest possible detail. So having finished with the noiseless case, we now come to the communication channel itself. The model for a communication channel, there is an input alphabet A, an element of A is transmitted through the channel, and then an external noise interferes, and then an output comes from B. And the noise is characterized in a statistical manner. Namely, if you send the symbol X, the probability, that is, if the input is X, what is the probability of output Y? That is given by nu X Y in my notation. So nu xy is the input output channel matrix, probability matrix, as x varies in A and y varies in B. Now I choose an input according to some probability law, say, and denoted by lambda. Then the joint input output distribution is given by omega, namely lambda x multiplied by nu x y. Probability of A multiplied by probability B given A, that is the rule. And once you have a joint distribution, you have the two marginals. The marginal distribution of the output is the output distribution. So there are three things: input distribution, output distribution, and the joint input output distribution. So there are three alphabets: A, B, and A cross B. Each one of them provides information. So you have H lambda, H mu, and H omega. And the quantity H lambda plus H mu minus H omega is a very fundamental quantity of classical information theory. Again, this was introduced by Shannon in his celebrated 1948 Bell system paper. Why is it so? Why is it important? The same quantity I have written in detail below is equal to H of output minus H of output given input and H of input minus H of input given output. It means once you know the output, that is once you have a knowledge of what you have received, then still some information is contained in the input. So H input given output, that is the information contained or uncertainty contained in the input even after knowing the output. But if you throw away that from the information contained in the input, then what is remaining is the knowledge that the channel has given to you about the input. So this quantity H lambda plus H mu minus H omega is information transmitted by the channel C about the input. There is a famous property of entropy, namely it is a concave function, and you have H of the average minus average of the H's, so it is always a positive quantity, non-negative quantity. So for different input distributions, the channel gives you the information transmitted by the quantity which I have described gives you the information transmitted about the input. Now you take the supremum over all possible input distribution which is under your control. Then see what is the maximum information that the channel can transmit. So this is more a philosophical description, it is not a technological description. So Shannon called this quantity the capacity of the channel, namely the maximum possible information about the input that the channel has the ability to transmit. So that is a philosophical quantity, but then Shannon followed it by a technological theorem. And what is that? It is one of the revolutionary theorems, not only in communication theory, but for the whole of mathematics, because it's a long story into which I cannot go, because the ideas of which Shannon introduced became fundamental in understanding many problems of classical mechanics, particularly about the stability problems, the three-body problem and all that. So it is not only important for communication theory, but also for the whole of physics. Now, what is the revolution introduced by Shannon in 1948? Because to understand the quantum revolution which is supposed to come, it is important to understand what the classical one is, because the quantum coding theorem is a generalization of the classical coding theorem. So what is that? So now you know the channel. The channel has an input alphabet, an output alphabet, and a channel probability matrix. Now I introduce what is called a code of size m and error probability less than or equal to epsilon. What is that? It consists of x1 f1, x2 f2, xm fm, where x1, x2, etc. xm are elements of the input alphabet. f1, f2, etc. fm are disjoint subsets of the output alphabet, and with the property that the probability of receiving the output in the set fi when xi is sent is greater than or equal to 1 minus epsilon. Every one of the pair every one of these pairs xi fi must fulfill the condition that if I transmit xi, it will be, the output will be located in fi with probability exceeding 1 minus epsilon. And the f1, f2, etc. fm are disjoint. So I have a good decision rule, namely I have the subsets which are disjoint f1, f2, etc. fm. If the output falls in fi, you decide that the message xi was sent. That is the advantage of having such a code. Then the probability of going wrong is less than epsilon. So this is a fundamental concept. Code of size m and error probability less than or equal to epsilon. Now you consider the maximum possible size. For a given epsilon, consider the maximum possible size. This is a function only of the channel probability and the number epsilon and nothing else. Right? So we would like to have an estimate, we would like to have an idea of this number. Now it is a very, so NC epsilon is the important number, maximum possible m, so that code of size m and error probability less than or equal to epsilon exists. And the inequalities are very messy. I have removed it from the transparency. So I am presenting only for what happens when you go on making repeated transmissions. So that means the channel is used again and again. That means from the channel C, I go to C to the power n. Then look at the number nc power n epsilon. So that means I am using a block of length n and transmit it run through the channel. Then I want to have an idea of the maximum possible size of the code. Interesting thing is this size grows exponentially. So if you use more and more the channel, then you can send more and more the information. So take the logarithm of that and see how it behaves. Earlier I introduced a philosophical quantity based only on the notion of entropy. And now look at that particular number C, which I called the Shannon's capacity. Then the logarithm of the number nc power n epsilon minus nc divided by root n. And then consider limit inferior and limit superior and see the band in which it lies. I have given some numbers. Sigma, what is sigma? Here, for each input distribution, I have a sigma lambda squared. I have a number, and then you consider sigma squared equal to sigma lambda squared for that distribution where the supremum is attained, the capacity is attained. See, earlier I defined the concept of capacity as the supremum over input distribution. Everything is happening in a finite set. Yeah, all the functions, entropy and other things are continuous. So supremum is attained somewhere. So there exists a lambda at which the maximum is attained. Look at that particular lambda, and that has the fluctuation sigma lambda square, and I have denoted that by sigma square, and that enters the the fluctuation band. Kappa is a universal constant. It is 2e inverse log e to the base 2. A and B are the sizes of the alphabet, capital A and capital B. So, in terms of well-known quantities, you see where the fluctuation lies. As a special case of that, the logarithm of this divided by n, that converges to C. Shannon proved in 1948 that it is greater than or equal to C, and we had to wait till 1960-62, by which time the famous book of Wolfowitz, Coding Theorems of Information Theory, appeared, and that gives a complete this theorem. But if you have understood the quantum coding theorem, you have already understood this theorem also, because the quantum theorem is more general. So you need not, without knowing classical information theory, you can make the quantum jump and learn the proof of the classical theorem at the same time. So what is the, of course I have used only product channel, but there are umpteen generalizations for which I shall give you the reference. But this is the fundamental theorem of Shannon-Wolfowitz, the story of classical information, coding theorems of information theory from 1948 to 1960. The interesting thing about this subject is that the only knowledge you need is finite dimensional vector spaces, spectral theorem, Chebyshev's inequality in probability, and then you have a wide open space of open problems. So for PhD students, this is a very good subject. You don't need to read too much. Now I introduce what is called elementary CQ channels. CQ means classical Q, classical quantum, because the information I am sending is classical, but the devices I use are quantum. So that is why this is called CQ. Of course, quantum information through quantum channels, etc. There are many open problems from a philosophical point of view, from a technological point of view. There is a large amount of literature which you can get through surfing the net. But I now go by the historical order of the subject. So what is a quantum channel? A CQ channel. Earlier I denoted the channel by script C, but now I have put a suffix Q. The alphabet A, that is classical information, that is the classical alphabet A, namely a finite set. But output alphabet is quantized, because what you are going to read, measure, do, play with, that concerns quantum system. So there is a Hilbert space. So input is an alphabet, output is a finite dimensional Hilbert space. Of course, as a lot of information flows, you have to understand that the size of the set A will grow, the size of the Hilbert space also will grow. So we can also grow, right, with our knowledge, with our research. So I have A, and then earlier I had nu x. So for each given x, nu x was a probability distribution. But now my output space is a Hilbert space. So for each x, I have a state rho x. So I have put here rho dot. For each x belonging to A, rho x is a state in the Hilbert space H. So that is the CQ channel. So now, following Shannon, we want to express what is a code. A code, now there are two different kinds of codes when you come to quantum theory. This is because in quantum theory you can make what is called a von Neumann measurement, and you can also make a generalized measurement. And the relationship between these two, there is a lot of, again, in the theory of measurement, there is a lot of philosophy behind this. And because of that, there are also open problems for students, because that is the future, where we don't know we don't know what is going on. So what is a quantum code of size m and error probability less than or equal to epsilon? It is m pairs x1 e1, x2 e2, xm em, where xi are elements of A, the input alphabet. E1, E2, etc. are positive operators lying between 0 and identity, but there is some total E1 plus E2 plus etc. plus Em that is less than or equal to identity. The advantage of this is that I can interpret this as a generalized measurement. E1, E2, etc., Em are positive operators. I minus their sum is an extra bit. It is like in the old case, you have a set and you have F1, F2, etc., Fm disjoint set, and the complement of their union, that is an extra bit, that is a junk bit, right? So you have a partition of set, but instead of partition of a set, you have partition of the identity operator. If it is going to be a von Neumann measurement, as it happens in quantum computing generally, then E1, E2, etc. are all projection, mutually orthogonal projection. So in the generalized measurement, these are positive operators whose total is less than or equal to identity. And what do you mean by error probability less than or equal to epsilon? That means trace rho xi ei greater than or equal to 1 minus epsilon. In other words, if I make the generalized measurement, suppose I have sent this trace rho xi ei greater than or equal to 1 minus epsilon. If you make a measurement where the outcomes are 1, 2, 3, etc., m plus 1, and that is characterized by the generalized measurement, namely E1 positive operator, E1, E2, etc., Em and identity minus their sum. And if you make such a measurement, what is the probability of the outcome I? Trace rho xi ei. So, and that probability should be greater than or equal to 1 minus epsilon. So that is the notion of a general quantum code coming from a generalized measurement. Von Neumann code means EIs are projections. But a general quantum code is as I had described. Once again, now as before, for imitating Shannon, I introduced this quantity, the von Neumann entropy of sigma lambda x rho x minus sigma lambda x s rho x. This is the quantity which I had earlier, the information about the input contained in the output. Information about the input contained in the output state. So this quantity symbolizes, that is usually called the Holevo quantity, and of course you can, in the final reference that I give, there is a more leisurely description by reading which you can understand this famous Holevo quantity. It is a fundamental quantity of quantum information theory. And of course it is an imitation of the Shannon's idea, namely the von Neumann entropy of the convex combination of the mixed states according to the distribution lambda x minus sigma lambda x s rho x. Once again, von Neumann entropy is also concave as Shannon's entropy, and therefore this is a positive quantity. S of the average minus the average of the f's is greater than or equal to 0. That is concavity property. Then you take the supremum of all this over all possible input distributions. That is what I have called it here as Holevo capacity. Just as you had Shannon capacity, now you have Holevo capacity. Then you have the theorem. The Holevo capacity is additive, like Shannon capacity, namely if I use two channels independently and consider the Holevo capacity for the joint channel, then that is equal to the sum of the capacity. When you come to communication of quantum states through quantum channel, the additivity property is still not known. It is an open problem of the subject. So it has this additive property. So if I use the channel n times, then the Holevo capacity Cq power n is n times C, this quantity. So this is a philosophical quantity. So you want a corresponding, that is this is entirely in terms of input distribution on the states. But now I want to relate it to the code, size of the code. I had earlier defined the, okay, now look at the following. I had earlier defined the quantum code of size m and error probability less than or equal to epsilon. Consider the maximum possible size m. That gives you a number. That is by capital N CQ epsilon. Now I can state the final theorem. Now look at the logarithm of the maximum possible size for n repeated uses. That is the enlargement of CQ tensor to the power n. That means A becomes A power n, the Hilbert space becomes the n-fold tensor product, and when you have a string in A power n, a word from A power n, x1, x2, etc., xn, then the corresponding state is rho x1 tensor rho x2, etc., tensor rho xn, right? Everything is growing. Now look at the logarithm of that, minus n times the Holevo capacity divided by root n. Then limit inferior and limit superior of this normalized quantity lies in a band, and that band is characterized again by some numbers. A kappa is a whenever I use kappa, k, they are universal constants. A is the size of the alphabet, D is the dimension of the Hilbert space, and you have the quantity depending on epsilon here. So the band is given by this, and if you take limit inferior of this n tending to infinity, that is equal to Ch. So this is the analog of the Shannon-Wolfowitz theorem. Now when you come to the proofs, Holevo's papers contain a little bit. Nielsen and Chuang's book, Quantum Computation and Information, that proof is also a little fuzzy. If you try to understand, you will have lots of difficulties in trying to understand it, and it is also incomplete. And then finally, in 1999, Andreas Winter wrote a PhD thesis with a completely clear proof of this theorem. And here you can have an idea of the rate of convergence, the speed of convergence is O of 1 over root n. So it is to be called Holevo-Schumacher-Westmoreland-Winter theorem, right? It has gone through a lot of effort. For von Neumann codes, we don't have a theorem. That is, if I restrict myself to only projective measurements or von Neumann measurement, of course the capacity will be less than or equal to Ch. But is it equal to Ch? Can you achieve whatever you achieve by generalized measurement? Can you achieve by von Neumann measurement? I don't know the answer. And in all the literature that exists, we do not have a clear picture. So, and whatever way you prove, it will be a deep analytical fact. Now I will give you a few references. For a detailed proof, starting from classical information theory and making the transition to quantum information theory, and finally arriving at this coding theorem, the last theorem. I have written the notes of all the lectures that I had given in the past in this, which came out a few days ago, this particular book. And I have brought a copy as a gift for the Dayalbag Educational Institute Library, because they have invited me to give this talk. In return, this is the only thing I can give. And for classical theorems, coding theorems in maximum generality, if you want, there is a translation of a book in Japanese. It's a very difficult book. This book is by Tae Sun Han, translation from Japanese, published by Springer 2003. For a comprehensive and leisurely account of classical information theory, the standard book used by engineers is Cover and Thomas. Mathematically, quite interesting book on this is by two Hungarian mathematicians, Cizar and Korner. I can leave, maybe you can make a copy of this. And then there is this famous book of Wolfowitz, Coding Theorems of Information Theory, quite a terse book. And the quantum coding theorem, as I have presented, it is from the thesis of Winter, but there is the main result is also published in IEEE Transactions 1999. Nielsen Chuang is the standard reference for all problems of quantum information theory, the second half of the book. There are many other interesting topics associated with this subject, namely quantum error correcting codes. On quantum error correcting codes also there is a book, but it is almost unreadable by some 4 authors. So one has to write it in such a way that undergraduate students can easily read like a novel. That effort it may come from Dayalbag Educational Institute. So with these words I conclude my one more reference. The latest reference which I could get on what I have spoken is from the net. It is this, September 29, 2006. That gives you the latest picture, namely it is an improvement of the theorem. The theorem which I got stated was for product channels. But if the channel has memory, you cannot have product. You will have correlations between the successive that is, all the states that you will get, they won't be product state, but there will be correlations there. So there is a generalization to that case in this particular article.